Yes.
Okay. Okay, first of all, I'd like to thank everybody's patience, especially Professor Hossain's and Dola Zaha's for my tardiness today. I'd like to welcome you all to the AI and ML Security Special Interest Group seminar series, virtual seminar series that we do once every month. This will be the last one for this semester, and then we'll reconvene after the summer again in September. So quickly to introduce the AIML Sec IG group, we are at least 260 plus members right now in LinkedIn. You should be able to find us in the LinkedIn group via that LinkedIn here, the link in here. You can also search for us with our new name, which is AI and ML Security IG. This slide is not yet updated, but it will be soon. We will have this talk recorded for you all to see later and look something like this, where we have some of the older talks listed here. So you'll just see the later ones as we progress through the months, right? So the logistics of the talk, everybody is muted on entry. Please stay muted throughout the talk, but then you can always type your questions for the speaker in the chat box anytime during the talk, and this will be read out by the moderators at the end of the talk, and Professor Hossain will answer those. Quickly to introduce Professor Hossain, who really doesn't need any introduction. He's very illustrious researcher in this area. He is an IEEE fellow and a professor in the Department of Electrical and Computer Engineering at University of Manitoba in Canada. He is a member of the College of Royal Society of Canada, a fellow of the Canadian Academy of Engineers, and also a fellow of the Engineering Institute of Canada. He was elevated to the IEEE Fellow for his contributions to spectrum management and resource allocation in cognitive and cellular radio networks. He has won several awards, including the 2017 IEEE ComSoc Best Survey Paper Award, 2011 ComSoc Fred Ellersick Prize Paper Award, and he is a IEEE ComSoc Distinguished Lecturer. He has also served as the elected member of the Board of Governors of the IEEE Communication Society, and this is only a few of his achievements. I definitely encourage you to look at his bigger bio if you'd like to know more about him. Without making any more delays, I'd like to welcome Professor Hossain to give us his talk. Thank you.
Thank you, Suba, for your generous introduction. And thank you, Dola, for organizing this talk today. I am really very glad and kind of feeling nervous to see a lot of our esteemed colleagues, have joined this talk today. So anyways, I'm going to start my talk. I'll go right away to the talk. And as you can see, this is on federated learning in a cellular wireless environment. This machine learning and distributed machine learning in particular has attracted a lot of attention recently, and there are a lot of research going on. And federated learning, which is a class of distributed machine learning, in particular has attracted a lot of attention in our communications community, and people have been started using these for optimizing wireless applications. And also there is another stream of research where wireless network itself is being optimized for an efficient federated learning. So anyway, let me show you the outline of this talk. I will first talk about very basic
Ekram,
about.
I think you have to share your screen.
Oh, sorry. I thought it's. Oh, sorry about that. So I thought it's being shared. Sorry about that. Just give me a second. I thought it's
That's okay. Today is a day for technical difficulties, apparently. So
Yeah.
I think when Suba, I think after her slides, I should have switched. So anyway, so here is the outline of the talk. I will start off with some basic information about distributed machine learning and how does FL, the federated learning, falls into the distributed learning framework. And then I will talk about the federated learning problem itself and a modification of the federated learning algorithm that we have developed in our recent work, in one of our recent works. That's what I'm going to talk about. I will touch on some of the convergence properties of the proposed algorithm, and then some simulation results before I conclude. Okay, so as you all know, artificial intelligence and machine learning has found a lot of applications, including communications in many cyber-physical systems, etc. Generally, in conventional machine learning, we have to train a machine if it is data-driven, supervised or unsupervised learning. We gather all the data at a central location, say a server, a data center, wherever. So we gather all the data, and then we basically train the machine, and we develop our machine learning model. However, we all know data is generated in different places, in the sensors at different parts of the networks. So bringing them all to a server is an issue, right? The server has to gather all the information, so that may not be an easy task. And also, besides communication overhead of bringing all this data to a server, there could be issues such as privacy issues. Maybe some of the sensors, some of the data sources may not want to reveal their identity. So gathering all the information at a central location may not be possible. And also, there could be a constraint on the server itself. It may not be feasible to bring all the data because data size is very large. So this has motivated researchers to think about distributed machine learning approaches where data could be distributed, or even the model itself could be distributed. So distributed machine learning is basically machine learning in a distributed fashion. And there are two flavors of it. One could be like data parallel distributed ML, and another is model parallel. So what is data parallel machine learning, distributed machine learning? So in a data parallel approach, the whole set of data is divided among a set of distributed servers, distributed agents. And each of the agents there runs the same training model. So it's just like data is distributed across different agents, and all of the agents, they run the same machine learning model, the same neural network, for example. In the model parallel approach, uses the same data for all agents. However, they work on distinct portions of the model. Maybe it is the case that the model is too big. It's a huge, gigantic neural network, maybe, which may not fit into a single machine. So the model itself is distributed across multiple agents. So this is a model parallel approach. So in this talk, I'm going to talk about more like the data parallel approach. The model that we're going to discuss is basically falls into this, the first category here. Okay, so this data parallel approach, so you have central data, like data in a location, in a server, and there is an entity which is called the parameter server, which distributes the data among the agents, right? Among the distributed servers who will run the same model. Or the data could be at distributed locations, say, for example, at the sensors maybe, right? So in this case, the data don't need to be transported or communicated from a central location to the distributed location. They could be already available at the distributed locations, as I said, say, for example, in the sensors. And basically those sensors, could be like an agents, right? So they run an ML algorithm, maybe a neural network, right? And everybody is using the same model, right? So that what is federated learning about. So data is distributed um, in the agents, right? So it's not coming from a central location, and the agents will basically run a ML model. So as you can see here, federated learning is a class of distributed machine learning, right? Where data is located distributedly, and all the agents run a same machine learning model. Okay, so this is basically the first category where the parameter server, like the central location, the repository of the data, it will send out the data to the different agents, the different distributed servers, and then they will run the model. The one that we just saw, like on the left side, right? The left branch, right, where the data is located centrally and that is allocated to the distributed servers, right? So that's the approach is shown here. The other approach on the right in the previous figure is the federated learning. As I said, I'm kind of repeating. The data is in the sensors, in the mobile devices, for example. So they have the data already and they learn the machine learning model. Now, in case of federated learning, there is a global model actually that has to be learned, right? So I will show you specific examples. What do you mean by global model? And to learn the global model, inputs are required from all of the distributed agents. So in this figure here, for example, say mobile devices, they have data, they have sensors. So the sensors, they generate data and they run the machine learning model. Everybody's running the same model, right? And the objective is to learn a global model. And periodically, they will feedback their updates on the model parameters to a central location, say, for example, the base station. So the base station will collect the model updates from all the distributed servers and aggregate them. And then it will broadcast the aggregate model parameters to the distributed agents, and then they will start working again on that global model broadcast by the base station. And again, they will feedback to the base station. Base station aggregates the model updates and feeds them back to the distributed servers, the distributed agents. And so it goes on like this. Okay, so this is what is federated learning. So here is an example. Say the task is to predict the next word based on a small amount of text, right? So each of the mobile users, right? Each user is sending text messages. Maybe you want to develop a model to predict the next word. So maybe the base station wants to know, or some control central location, it wants to predict the users what would be the next word, like in this kind of text messages. So basically, each of the mobile user can have it inputs on this learning process at the central location. And this is an example, actually one of the early examples where this concept of federated learning was used. I will mention about other applications more on the mobile or wireless networking side. Just give me a few minutes. I will show you more applications. So to summarize what I have said, distributed machine learning schemes that rely on data from multiple end users suffer from the privacy leakage issues. So there could be problem in gathering all the data from distributed sources due to the privacy issues. So that kind of motivates the use of federated learning. And as we have mentioned, federated learning does not require migration of data from the end devices. So it's good. You don't consume energy, etc., to transmit all the data to a central location. And it involves local learning model computation at the end devices. As I said, each of the end devices will calculate basically the model parameters locally, and an aggregator, a central location. So for example, the base station can collect all the inputs from the end devices to update the global model parameters. Yeah, so basically this is a paradigm where many clients, they collaborate to train a model under the orchestration of a central server. So we need a server in this case. In fact, this is what is also called a centralized federated learning, because we need to have an aggregator, a server, which will collect inputs from all the distributed agents. And I can tell you, there is also another flavor of federated learning, which is distributed federated learning, which does not require to have an aggregator. So that's also possible, actually. Yeah, so here it is. So in the centralized federated learning, all the clients, all the distributed agents, they collaborate through a central server, while in the distributed federated learning, there may not be any central server, but the agents, they will communicate in a peer-to-peer fashion, right, to learn the global model. Again, we will be talking more on the centralized federated learning. The distributed one is a very new area, I should say. And there are a lot of interesting problems which have not been addressed. But people mostly are working in the CFL, the centralized FL area actually these days. Okay, so here is again how this centralized federated learning works. So we have a global model. So it could be, for example, say you are trying to learn a regression model, right? Now the data is distributed across the agents, right? So for a regression model, you need those model parameters, right? So you want to learn those model parameters based on the inputs from the distributed agents. So the agents will calculate those model parameters. Say, for example, the gradient, for those parameters, I mean, gradient for the loss function maybe, or, right, which will be used to update the global model parameters, right? So those gradients, for example, will be sent to the central aggregator. Aggregator will collect the inputs from the distributed agents, right? And then it will update the global parameters before it's broadcasting again to the distributed agents. So they will initialize those model parameters based on what they receive from the base station. And then they again use their local data, right, to obtain, for example, the gradient of the parameters. And then they send back to the server aggregates. So the process continues like this. So the applications in the wireless context, in the communication context, for example, there could be edge computing and caching problems where you may want to develop model on content popularity, maybe based on the user and content interaction. You may want to develop some prediction models for user preferences, maybe for caching, for example. So in all those cases, you may be able to develop some FL model. And one, I think, for us who work in cognitive radio or dynamic spectrum access, spectrum management, for example. This is, I should say, very nice application, quite kind of natural. So often we want to develop prediction models on the spectrum utilization, which spectrum bands are being used so that we can use the spectrum holes, right, etc. So based on the distributed, basically, knowledge, right, on the different devices, for example, we may be able to develop a global model to predict the spectrum availability, spectrum utilization, and accordingly, we can have models for spectrum sharing. So it's like exploiting distributed intelligence, somehow in the spectrum management. Also, other problems related to prediction, for example, traffic prediction in vehicular networks, smart navigation. Again, the idea is to employ like a distributed intelligence, like you have data at the distributed locations, at the devices, the vehicular nodes, etc. And how do you basically exploit those data, right? Without getting all them in a central location and learning some machine learning model, but rather you keep the data locally and then try to learn your prediction model or a global model. Okay, so now when we talk about federated learning in a wireless or unreliable communication environment, we must take into account the fact that the connections, for example, between the distributed devices and the central location, right, the aggregator, for example, is unreliable, right? And also there are bandwidth constraints. We cannot have all the devices participating in the process at the same time, right? And of course, the devices have different characteristics, different capabilities maybe, because the devices could be heterogeneous. So their processing and computation capabilities could be different, right? And the data most likely to be non-IID. I mean, so the data that the devices, they gather, they basically, the sensor data, etc., they may not be IID, right? So all these things are practical considerations that need to be taken into account when developing an FL model, right? So the world is not ideal. I mean, you got to take these non-idealities into account. Okay, so now if the bandwidth is a constraint, right? So among all the agents, I mean, you cannot afford to allow all of them to participate maybe at the same time, right? So you need to do some modifications in the basic FL procedure. So the server can only receive inputs from a group of users, right? Because the bandwidth constraint. Okay, so what the server will do, it can sample a group of devices and then basically broadcast the global parameters, right? Say for the regression model, those model parameters to the selected devices, the devices which it has, I mean, scheduled, for example. And then each of those selected devices will initialize their model with the global parameters that the base station has sent, and then it will start doing its local processing, local computation. And then after it gets the gradients, for example, right? Based on its own data, it computes the gradients, and then it will send this to the server, and the server aggregates, update the model, right? And then it again, in the next round, the next iteration, it will choose maybe another set of devices. So now I can mention, so this is itself a problem, and how do you select the users, right? So the scheduling problem will be an important problem here. And the problem is actually how to select the set of devices which may make your algorithm converge faster, right? I mean, and first of all, whether you really converge to the basically desired model. I mean, it should not give you something very different than what you expect, right? And also how fast. So accuracy and the rate, right? So you want to arrive at the global model, which is accurate, not too far from what you expected, what is the ideal, optimal, and also not should not take too long to converge to that model, because if it takes too long, it means you have got more overhead in terms of sending all this information and iteration, computation, etc. Right? So accuracy and speed, right, and the rate of convergence, that will be important, and that should affect the selection of the devices here, the scheduling of the devices. Okay, so traditionally, existing works in the literature, they assume that the server receives the updated local parameters from all the devices. There is no constraint on the bandwidth maybe, and everything is good, ideal, there is no error, etc. But which of course is not true in a real world um, scenario. And what will happen in a real world scenario, say a base station and there are 5 devices who are basically participating in this federated learning process. So the devices which are close to the base station, for example, have a better channel quality, and they most of the time they are successful in sending their updates. So what will happen, the final model will be is more likely to be biased towards basically those cell center devices, the closer devices. So whatever their inputs are, they will affect more on the ultimate final model. So it will be more biased, right? So, and basically it can end up with a very inaccurate kind of model. So this is a real problem that needs to be solved. So in this work, I shall mention about a very simple idea. Idea is very simple, and it basically solves this problem. So you basically, you take into account the effect of the bandwidth limitation and the error in the wireless channels. But still, you can arrive at a quite accurate global model solution for your global model. And basically, it converges. Okay, so this is a layout that we consider. So you got this random point process model where the base stations, they form a homogeneous Poisson point process, and devices are uniformly distributed in each cell. Say n is the, at some time period, say n is the number of devices in each cell, and m is the number of resource blocks that are used by the devices to send their updates to the base station. So m is less than n. There will be more users than the number of resource blocks that are available. So now the FL problem is as follows. So you have a global model. Say it's a global loss function, right? It looks like this. Now you can basically express this global loss function in terms of the local loss function. So this is, I think, easy to see here. So you have got n devices. Okay, you have got n, big N is the number of devices who are participating in this federated learning process. And the total number of data that you have across all the devices is small n, right? So this is how you express your loss function. And at the end, I mean, you can express it in terms of the loss function at each of the devices. So it's like a weighted loss function, right? So W is the model parameter that we want to learn, right? And PK here is a weight that we give to each loss function at each of the devices, and summation of PK is 1. So so basically, we would like to find W, right? That minimizes FW, the loss function. So this is the loss function, and we want to minimize it, and we want to find the corresponding W value. Now, of course, minimizing FW is equivalent to minimizing this summation, right? So we'll see the relationship, like how, if we take a iterative process, how can we update the parameters W, right? In terms of the parameters of the local devices that you get from the local devices. Oops. Okay, so yeah, so for example, a loss function could look like this. Say for a linear regression problem, for example, the loss function is like this, right? So, so this is a global loss function, and the local loss function again, in terms of, say, at device K, you have got Nk data, right? So the loss function is like you take the average, right? So average value of the loss function. So when you evaluate this for each of the data points, and then you take the sum and then divide by the number of data points, so you get the average value of the loss function, right? At that device. Okay, so I think I'll just skip this. Okay, so this is the relationship here that I was mentioning. We want to minimize the global loss function, right? So, and which we express is like this, right? So this the global loss function. So if we take the gradient of this, if we take the gradient of the global loss function, so we can express in terms of the gradient of the local loss function, right? So so then if you want to do a gradient descent algorithm, so basically we'll update the global parameter like this, right? So if you are familiar with gradient descent algorithm, you know this is how we update the model values, right? So in your next iteration, the W will be updated as follows. So the current value, and then it's a gradient descent, right? So this is the lining parameter eta, right? And then basically the gradient value. So because the loss function has the gradient value like this, right? So this is the gradient value. So you basically multiply the gradient value with the lining parameter and you subtract from the present value. So this is what we'll be doing. And if we keep on doing this, then after a while, it should converge, well, depending on the gradient. There's some properties that need to be satisfied for convergence, but hopefully it will converge and we get our model parameters. So what I'm trying to emphasize here, the global parameters can be updated based on the local inputs. You see the local gradients are here, right? These are the local gradients. So if we collect the local gradients, at the central location, we just use this equation, right, to update our global parameters. So this is the basic federated learning. That's it. So the federated averaging algorithm, this is called the federated averaging algorithm, and this is what it is. So from each of the devices, you get the gradient, you collect it, and basically you sum them up, and you give a weight depending on the proportion of the data points that each of the devices uses, right? And then you use this basic gradient descent equation. So this is what is the plain, I mean the the simple federated averaging algorithm. But then what we are saying, in reality, it will not be like this, because these local gradients, not all the devices can send their gradients because you have resource constraint. And even if some device has the resource, is allocated a resource block to send the gradient, maybe it fails, right? The transmission can fail, right? So we need to take this into account. So the algorithm needs some modification to take into account the bandwidth limitation and the communication errors. Okay, so this is the problem that we are dealing with. Okay, so again, I'm writing the equation here. So this is the equation, the gradient descent equation that you use to update the global parameter. And just by noting that at each of the local device, you see, this is the local update, right? This is the local update that you do at each of the devices. And this guy here, nabla fk, right, is basically wt minus wt plus 1k. So this equation here, this equation, the first one, the top one, you can rewrite like this. So this is just another way to write the iteration, right, for updating the global model parameters. Same thing. So this equation is same as is the first equation here, right? So again, what we are saying, each local device needs to basically send this difference, right? Like it sends the difference in the local updates to a central location, and the central location will just do this, follow this equation to update the global parameters. That's it. So that's the federated averaging algorithm. Just another way to express the update equation. Okay, so as I said, due to the scarcity of the resources and the unreliability of the channels, not all users will be able to, send their updates. And we get to do something about this. So we get to first schedule, right? So among all the n users, for example, in a cell, we may not be able to accommodate everybody. So because we have got m resource blocks, m is less than n, so you go to first find a subset of those users, right? And then we got to also remember that even if a device is allocated resource block, her transmission could fail, right? So that has to be also taken into account. Okay, so we cannot just use the naive federated learning algorithm because it may fail. It may give us a very inaccurate model at the end. Okay, so what to do? Now, this is, as I said at the beginning, this is a very common sense idea. So say among the scheduled devices, right? The devices which have a higher success probability, right? They will be successful more often to send their updates, right? So somehow we got to basically give lesser weights to those guys compared to the other devices which could suffer more losses, right? During transmission. So because those guys get fewer chances to basically to give their inputs to the aggregator, right? So the idea is give a more fairer chance. So basically give higher kind of weight to those updates that are coming from the devices which are in a bad channel situation. I mean, whose channel conditions are poorer. So that's the basic idea, okay? So so that's what we will use to update basically that basic equation for global model updates. Now, just to quickly show you how this proposed algorithm will work. So the base station will sample a group of devices and it will broadcast the global parameters, right? And then each of the devices, they will do local update. Now, they could do once or maybe a few, right? So k updates maybe, right? And then they will send those updates that gradient, for example, or just the difference, right? Between the initial and the latest weight value, for example, to the base station. The base station will aggregate following that equation that we saw, right? And then it will send back that model parameters W, and every device will initialize with that global value, and then start using its local data again to generate the gradients. K iterations, send back. So that's how it proceeds. Okay, so it's actually E here. So E is the number of local updates, steps in each round. Okay, so it's E here. It's not K, it's E here. So before it sends the update, you will do like an E number of iterations. So it's simple. Okay, so I think I don't need to repeat. I have already mentioned all of these steps: sampling, broadcasting, and you do a local gradient update. E steps, right? And then you send the difference values, right? And that will be used by the base station aggregator to update the global model parameters. Okay, now, so the main trick here, right, in the aggregation step, right? So this is the main kind of idea here. So as I said, in the aggregation step, you give more weight to the devices which are more prone to errors. So this is exactly what we are doing. So it's not just taking, for example, just this difference. No, it's not just taking the difference, but you get to give a weight according to the channel condition and also the chance for a device to get a channel. So that's what we are doing here. So in the denominator, UK is actually the average success probability for a device. So the higher the probability of success is, the weight will be lesser. As I said, I mean, we want to be more fair, right? And again, QK is the probability of allocation of a resource block to a user. So the higher the chance of allocating a block to a user, the weight will be correspondingly lower. Okay, so that's the idea. And of course, in the numerator, I mean, you take that input into account if that update is successfully transmitted. If it fails, it doesn't have any effect, right, on the aggregation. So we go to, in the numerator, we put the probability that the transmission is successful. But importantly, in the denominator, basically, we put the average probability of success in the denominator. So basically, the users who are closer to the base station don't dominate in the global model update process. So we want to make it more fair, right? So that's the idea. Anyway, so this is the same process. I don't want to repeat. Now, in the ideal case, basically, all devices can participate at each aggregation step, and all the transmissions are successful. Everybody has bandwidth, resource block allocated to send their updates, right? So, so this case is more general, which captures the ideal case as a special case. So the ideal case is more like a centralized optimization case. Okay, so now I give you an example, maybe it will make it more clear. So we take a toy example, say a regression problem, right? So, so we want to learn this model. So this is what we want to learn. So the V is the regression parameter, right? So the regression vector. So we want to, so you are given a set of data points and you have to find the best fit, for example, right? And that's what the regression is. So, so you find the best fit by minimizing the squared errors, right? So say you have got 1,000 data points, okay? And we have got 2 devices. Each device has 500 samples, okay? So P1, P2 will be 0.5 in this case. So what each device will do, they will try to minimize this sum of the squared errors, MSE, right, in its local data set. And these are the local values, V1 and V2 for each device, say V1, 1, right, V2, 1, and then V1, 2, V2, 2. So these are the local, local values for the model parameters, right? So, so now let's look at this figure here. So the 500 data points that we allocate to each of the devices, right? So say for device 1 on the left side figure, so leftmost figure, so these red dots, they're the points, right? 500 points. So, and this black one, this shows the regression plane, right? So that's the plane that we want to find out, so that will minimize the sum of the square errors. Now for the other device, say again the red dots are the points, right? And so regression plane will be like this red one here, right? Now they will get these 2 model parameters, right? Which describe this black plane and this red plane here when they're doing these 2 set of data. Now, if all the data were in a central location, for example, then the points will look like this. And this is the black plane that you will get, right? When you do it centrally. Now, our objective is how can you use these, these local model parameters, right? How can we aggregate the local model parameters so that at the end we can get something like this? So the model parameters at the end should give us a plane like this for our regression problem. So how do we basically the local values that we will get at each of the devices, how should we aggregate them to obtain at the end a global parameter that should give us this regression plane here? Okay, so so I think this example probably makes it clear what we are trying to do by federated learning. Okay, so at this point I'm going to show you a video, a small video actually, before going into this analysis here. So I will close this and I will share another video. Just give me a second here. That will kind of show an animation of how our proposed algorithm will proceed. Give me a second here. Okay, folks, so you see the figure here that I'm showing. So in this figure here, I will show an animation just for a few seconds. So this left two figure will show how with the proposed algorithm, how things progress, right, toward achieving the global model parameters. And the rightmost figure is with the conventional federated averaging algorithm, where we do not take into account the channel errors, etc., into account, right? So this will show, the animation will show you that, okay, with the change that we propose
Professor,
in the.
So we don't see the slide deck that you're showing. Currently,
Yeah, no,
we still see the same one.
No, I removed the slide deck, Dola, but I am showing an animation. Do you see that? No.
No, we are still looking at the same PDF.
Okay. So sorry. I think let me stop share, and I will share this. Yeah. Okay. Do you see
Yes.
something different now?
Yes.
Yeah. Okay. So what I was saying in this figure, I will show an animation shortly. So the left two figures will show how things progress with our proposed modification, like the local parameters, how they're aggregated and they kind of converge to the global parameter, okay? On the rightmost figure is the case where you do not use that modification, you use a conventional naive method, okay? So let me start this animation. Okay, so this will take quite a long. So you basically, so this basically shows the progress, as the iterations go. And if I move, basically, so at the end, very end, maybe I just stop here. So you see the final updates are very close to the global parameter. So this W star was our optimal, global parameters. Like if we solve the problem centrally by an optimization, like an regression problem, right? We solve it centrally at a location, so that's what we get. And in distributed case, we get quite close to that actually. You see for the left two figures. On the other hand, the rightmost figure, this is what we get at the end, which is very different, which is quite inaccurate because our optimal solution should be here, but we get something here, right? You see, so I think this, I'm trying to give you the kind of essence that the proposed modification actually works. And when we use that update algorithm for aggregation, at the end, we get model parameters, which are very close to the optimal model parameters that we would have got if we solve that problem centrally. Make sense? Okay, so well, this is like a 1500 iterations. I don't want to show the whole thing, but I think the essence is this. So the algorithm will converge and we'll get something very close to the global model parameters. Okay, so I will stop sharing these because I could not integrate with the slides, so I had to show it separately. So I will stop it and I'll bring back the slides now. Just give me a second here. So I'll bring back my PDF slides. So yeah, I'm showing it here. Okay. Okay, so Dola, I think you see the slides. Okay, so.
Yes,
right?
I see the slides.
Okay, so I have to quickly. Okay, so I hope I have been able to, give you the idea of this algorithm and to give you a kind of sense of the convergence for this algorithm. Okay, so now the analysis, I will not talk about all the details, but what I can tell you, there are some assumptions under which we can actually derive a closed form kind of expression for the convergence rate. Okay, these are kind of a typical assumptions. I mean, if you look at words, basically, you will see that they're like a common assumptions. First of all, these functions, the local loss functions have to be strongly convex, and they have to be L smooth. L is the smoothing parameter, mu is the strong convexity parameter. I will try to give you a graphical kind of sense of what all this strong convexity and smoothness mean. And also, if your variance of the gradients are bounded, and the second moment of the norm of the gradient is bounded. So you have to remember these parameters a little bit like a G here. Then with these 4 assumptions satisfied, okay, I'll go, we can get a convergence result that I want to show you, okay, like this. So this is basically the main result on the convergence of the proposed federated learning algorithm. Now, what is important here to look at the effect of the different parameters here. So G, as I mentioned, that's basically the bound on the second norm of the gradient, right? There are a few other parameters. E, for example, we know what does E mean. E is the number of local iterations at each device. And mu is the convexity parameter. L is the smoothness parameter, right? And T is like the how many iterations you have done so far. So basically the convergence rate is linear. So that's what all it says, because T is in the denominator here. So basically the algorithm has a convergence rate which is linear, okay? W0 is the global parameter. Now, one important other important parameter here is, okay, we talked about sigma k. This big gamma here. So what does this big gamma mean? I'm just trying to show you the parameters that are involved here in this convergence, like the parameters that affect the convergence. Okay, so what is this big sigma here? Big, what is called this gamma here? So big gamma is actually the difference between the optimal loss function and the weighted sum of the local loss functions. Just for your information here. So this gamma in the convergence formula basically is the difference between the global loss function, like at the optimal point, right? The value of the global loss function and the weighted sum of the local loss functions. Okay, so now, of course, if you have IID data, then basically the difference will be 0. So for IID data, when you have, say data distributed, IID data across all the devices, so this guy, gamma will be actually 0, but in general, it may be something non-negative actually. So it may not be 0. Okay, and basically it's easy to show that this gamma value is non-negative. Okay, so that what this gamma here in this expression for the convergence. Now, this is basically the smoothness and convergence property of the function. As I was saying, the function, the loss function has to be mu convex, L smooth for this result to be true. And this basically shows what does that L smoothness and mu convergence mean. So the function fx is something like this, so it is less than this function and is kind of higher than this function. So that's what we call fx to be mu convex. So if the value of fx is higher than this value here, and we'll call it to be L smooth if it is less than this function here, this orange, or what they call this pink function here. So, but what for us, quickly, if you want to see some nice observation here, what we see, for example, if say for example, if E increases. So if E increases, so what will be the effect of E, for example? What will be the effect of G, for example? Okay, one which is obvious from here, if G increases, the convergence will be slower because this right-hand side, the value of the right-hand side will be higher. We want to be small, right? So the smaller the value of the right-hand side, the better is the convergence. So G, B will make it higher, so the convergence will be slower. But E is a little bit more tricky here. We'll show the effect of E later on. And what else we can see here? Like, of course, this sigma case, if they are higher, again, the convergence will be poorer, right? So the point is we want the right-hand side to be small, right? So we can choose parameters that will make the right-hand side small to improve the convergence speed. Yeah, okay, so B, I did not define B here. So B is actually like this, and which basically shows we want B to be small, right? So which means if M is high, which will make B small, the convergence will be better, okay? And T is the KE, like a total number of iterations, you can say. So E is the number of local updates during each iteration, and K is the total number of iterations. So T is like the total time, right? So like a total number of updates, over certain time period. So of course, as T increases, the right-hand side will be smaller, so that will increase the convergence, which is kind of intuitive, you can say. Okay, so now I think I'll kind of talk a little bit about the simulation. Now this algorithm is also valid. The convergence properties are also valid if you do a mini batch gradient descent. It doesn't need to be like take only one sample at a time when you do the local update, but during each local, iteration, you can take a batch of data. So things don't change. So the convergence properties still hold with mini batch gradient descent. Okay, so that's what it says. So I want to repeat, go through all the details, but the same results hold. Now, quickly about some simulation results. So we basically test this modified federated averaging algorithm for both synthetic data set and some real data set based on this MNIST, which is very common. You may be familiar, I guess, on handwritten digit database. So we use both real data and some synthetic data. So these are the details about how to generate those synthetic data. So these are all like image data you can think of, like each data point is like a 60-bit, like 60-bit, like you can think of an image. And basically each image, each of these points is like an image and can be classified as one of the 10 classes, for example. So these are like an image data, and we have a label for each of these points. The label could be one among those 10, as I said. And these MNIST data, these also like you can put it as a single vector vector of size, I think 700 something, 784 image. So for the neural network, we use 3 hidden layers with 300 neurons at each hidden layer. And as I said, for the synthetic data, it's like an image. Each data point is an image of 60, bits maybe. And okay, this is like the specifics about the neural network. We have a ReLU activation function and a softmax output layer. Okay, so the point is, what are the performance metrics? So, so we want to distribute those data among the devices, say 50,000 MNIST images among the devices in a non-IID manner, right? And then we want to classify them, right? We want to design a classifier, for example. So we would like to see the accuracy, for example, right? And the speed that I was mentioning at the beginning, how accurately we can predict, how we can classify, and also how quickly. So the accuracy and speed. So these are the two performance metrics. Now, in terms of uh, accuracy, we actually consider two metrics here. One is called a cross entropy loss. If you are familiar, um, basically, this is how we calculate the cross entropy loss. Now, I give you a simple example maybe in the next slide. So what is this cross entropy loss? So say, for example, if you have images, right, they belong to different classes. So at the output of the neural network, right, the global model, we are trying to calculate the global model for the classifier, right? So the output of the neural network, say, when you put a 60 input bit image, and that image could belong to one of the 10 classifiers, right, or classes, right? So you get 10 values, for example, at the output of the softmax layer. And here, okay, for example, if you've got 3 classes at the output, right, and you get these values. So the cross entropy, like if the correct class for the image is, say, class 1, your cross entropy will be minus log 0.24, right? And your neural network produces these values and for the given image, and you know that, okay, the image belongs to class 3, right? Then the cross entropy loss will be this. Okay, so basically the higher the accuracy, I mean, the values that it generates at the output, right? And for the correct class, if the value is higher, you get a lower loss. Okay, so that's the physical meaning of this cross entropy loss. So you get the values, the probability values at the output, and the probabilities are higher for like a correct class, right? Then you get a lower loss. You got like a cross entropy loss will be lower. So this is what we use here for accuracy. And also we can do like a normal, accuracy measure, like a fraction of the predictions which are right. This is another, like I should say, simpler accuracy measure. So for both this accuracy, we observe the performance of the proposed modification. So I would quickly show you. I think I'm going over time. So okay, so for the real data set, we use 60,000 data points. We distribute across 100 devices. For the synthetic ones, we almost 41,000 samples. Again, we distribute them in a non-uniform manner. And okay, so here are the results for the cross entropy loss and accuracy. Maybe it's easier to see the accuracy. So you see almost like 80%, more than 80% accurate result we can get for both the data types, synthetic and real. And also the convergence. In terms of convergence, it takes probably 50, right? About 50 rounds when things converge, and we get a model which is like an 80% accurate actually. Okay, so yeah, that's the main observation here, and similar for different values of E. And I was mentioning the selection of E could be a bit tricky actually, and you can optimize the value of E. That's what it shows. So there could be an optimal value of E. So if E is 1 here, for example, like you do just one update for each iteration, so this is what you get. But with 5, it's like goes down. Loss is better, right? Accuracy is higher, right? So with E2 here, accuracy is poorer, right? So, sorry, it's 5 here. So this is a 5 here. The accuracy is poorer, but for 2 is better. 1, 2 is actually this one here, the top one, and 1 is the best here. Okay, so here 5 is the worst, right? 5 is the worst, and 1 is this one here, the solid one. 2 is the upper one. So actually 2 is the best here. So the point is there could be an optimal value of E. So you can choose E to have better results, better accuracy. In fact, if you look at the uh, like the expression that we show for the convergence, so that is not very evident, but when you run the experiments, then you see that you can find an optimal value of E. Okay. Again, similar, just for different values of the learning rate. And yeah, again, the same observation for different values of E. So you can choose E optimally. Yeah, so here basically I show probably more clearly like how does the convergence rate vary with E. So there could be a optimal value of E for which the convergence is the best. Okay, so folks, I think that's basically all that I wanted to say. So in summary, I have talked about an FL algorithm that is suitable for a wireless setup in a centralized, like a cellular wireless setup. And we have talked a little bit about the convergence. And basically, the idea is to incorporate the success probability in the communication as well as the channel availability in the algorithm so that we get a good, accurate result at the end. And also, actually, in this analysis, we used a large-scale analysis using stochastic geometry to calculate the success probability. So it takes the interference, etc., into account. And we have seen the convergence of the proposed algorithm, which is like a linear. And I have shown some experimental results based on the real and synthetic data set. Well, so this is a very fertile area of research. There are a lot of problems, especially when you go to decentralized, like a distributed FL. I don't think, to my knowledge, I don't know the very good work yet. So that's a good problem, but it's theoretically also very elegant. How do you do the convergence analysis? That will be more difficult to do, but that's a very nice problem to work with. So Dola, I think I'm sorry for I have gone over time. Now I remember what Homer said, when you try to be precise, you make yourself obscure. That's what he said. So that's my excuse to going beyond the timeline. I'm sorry
That's
about that.
fine.
Yeah.
That's fine. Thank you so much for this wonderful talk. This was very interesting. And we have quite a few questions. So let me start with the questions first. So this comes from Professor Marwan Kruns. Can you explain the significance of fairness in giving weights to different local servers / machines? And is there a higher value of getting one update from two machines versus two updated from one machine?
Well, that's a very good question. Thank you, Professor Kunz. So I think the idea is to improve the accuracy of our, the algorithm. In terms of achieving close to the optimal global parameter. So the one that we have shown, this is, I think, just one way to do it. But as I was mentioning, there could be other ways of achieving this as well. Maybe you do scheduling, because the one that I showed is just scheduling is done simply like by flipping coin. Like you have got m resource blocks and n users. So each user has a probability, like a uniform, random kind of probability to choose a user. But maybe you can make it more sophisticated. Maybe you can do even better. So there could be other ways to scheduling users, and maybe fair. But at the end, we want to improve the accuracy. So fairness. If it helps us to improve the accuracy of the algorithm, right? Because we want to converge to a value which is close to the global parameters, right? So that's what we want to do. But as I said, there could be other ways to do it for sure. And this could be an interesting, problem to think about. Sometimes, like there are actually a lot of problems. Like if you have quality of those updates maybe as well. Maybe a guy is a good channel, or a bad channel, we are giving him higher priority maybe, but his update may be useless. It's not very useful, right? So the quality of the updates may be also taken into account maybe. So there could be other considerations. Thank you.
Sure. So the next question comes from Majid Butt. Giving more resources to the UEs with bad channels is against opportunistic resource allocation, helping faster federated learning convergence, but suboptimal resource allocation. What about having a policy that balances these two extremes? For example, dedicate a smaller part of spectrum to call center learners and larger part to other learners to ensure better use of spectrum.
Okay, so this is a long question, but it depends on the objective, right? So we are not necessarily optimizing the wireless resource utilization here, right? Our objective is to improve the accuracy, right? So I mean, as far as I understand, what you are mentioning about is kind of doing a balance, right? I mean, maybe it's more expensive to try to be more accurate, right? I mean, or maybe we can sacrifice some accuracy by being more efficient in consuming the resources. So I think it depends on our objective, right? So as I was also mentioning at the beginning, there is a whole stream of research that trying to utilize the resources, right, while trying to achieve some level of accuracy. So I think the solutions will vary depending on how do you pose the problem, how do you formulate the objective, etc.
So
Majid, I hope I could answer your question. So.
I think it does.
Thank you.
The next question comes from Amor Nafka. How about if there are malicious agent trying to inject error in global model?
That's a very good question. I can tell you, recently there have been work where they use blockchain actually to send those updates. So basically you make it secured, right? So the devices who are sending the updates, make sure they are valid users. They're not malicious. So you can actually integrate something like a blockchain method here to make things secure. And very recently, I've seen a paper they're trying to do it actually in a vehicular setup. So it's very interesting. So of course, we got to deal with security here. Yeah.
Sure. The next question, Suba, do you want to elaborate on that?
Exactly. I typed too fast. What I was trying to ask is if somebody wants to work on problems like this on federated learning for applications that involve spectrum/wireless communications per se. Now we're thinking about running some applications on the wireless, but what if the wireless was the application? Do you have any pointers for good data sets?
Well, Suba, this is, I think, a complicated question. So, well, there are not many data sets. I mean, as you can see, people are using data sets from the traditional machine learning applications, right? The classification and things like those. But you are right. I mean, for wireless applications, may not be much, data sets available. But on the spectrum management side, there could be, data. Suba, you may know even better than me because there have been studies on these spectrum measurements, etc., right?
Yeah.
So on the spectrum side, maybe there are data sets available, but of course, in general, there are not many data available, and you may often need to work with synthetic,
Okay.
Yeah, thank you.
Thank you.
So the next question comes from Jingjing Yao. Could you explain what specific cellular network features do you use in your federated learning model?
Very good question. So first of all, we use like a random model, right? I mean, it's a large scale cellular network model where you take into account the intercell interference into account, right? Because we are using stochastic geometry analysis to calculate the success probability, etc. So it's a large scale model. And as I was mentioning, the base stations are modeled as a PPP. Their spatial locations are modeled as a Poisson point process. and we assume that the users in a cell are distributed uniformly. So this kind of assumption that we have used. So it's not just like a single cell, or so it's a large scale cellular model, and the success probability is like based on SINR models. We assume that okay, the SINR at the receiver base station is above certain threshold, then the probability is like an SINR based success probability, right? So we say transmission is successful if the is the probability that the SINR, basically the SINR is greater than some value, right? If that happens, that probability is the probability of success. So yeah, so these are the assumptions.
I think that I have a sort of follow-up question, but I think what Jing is talking about is what exact feature is probably the sensors are looking for, or what is being not just a cellular network. Is it like spectrum usage or traffic or
okay, I see. So you're talking about the application, right? Well, so I did not really mention a specific application, but it's more an abstract. You can say the base station is trying to learn a model, right? It could be on a spectrum usage, or so. It's like a generic model. You can say a loss function. You know, so I do not really talk about any specific application. So it's more like a generic kind of setup, yeah. But actually, this is also good because we need to really think about applications as well. And you see 90% of the work, you see they're using the traditional machine learning, those classification, image recognition, but more from wireless network optimization point of view, maybe like we can use federated learning to make the networks efficient, more optimized maybe. So that's what we can think about actually. So, but I can tell you there are not many works in that direction. So this is what we need to think about.
Sure. The next question again comes from Professor Kranz. In the presented examples, the global and local models are similar. What if your global model has more parameters than the local model at each device? Can federated learning help in this scenario?
Okay, that's well. I mean, I'm not sure whether I can answer it accurately, but I think the idea of federated learning is we want to learn the model parameters locally. If there are some parameters, exclusively for the global model, I mean, well, the local devices cannot contribute. So that has to be done by the central aggregator. I mean, so I don't think we consider that kind of scenario, and it's kind of atypical. I don't think people consider this kind of scenario. But then, I mean, those parameters which are not part of the local model, I mean, that are to be found out by the aggregator. I mean, so, there's no input from the other, yeah.
Professor Kranz, if you want to unmute yourself, please go ahead and do that.
Yeah, I'm not. Okay, let's see.
I think we can hear you.
Oh, sorry. Okay, it's just unmute. So hi, Ekram. What I meant to say is the following. I mean, we're dealing with situations where we have very, very large neural network. And again, this is in the context of wireless signal classification and inference. So I guess my question is whether it is possible to distribute the learning of the model by segmenting maybe the parameter space across various machines.
Oh yeah, I see. Okay, Marwan, I got your point. Actually, this is like a model parallel approach. I guess that's what you were referring to.
Correct.
Yeah. Yes. So yes, I mean that's possible, but I have to admit, I don't know much about, that paradigm. But as I was mentioning at the beginning, there's the other approach of exploiting federated learning when you segment the model itself, among the different agents. Yes, so theoretically that should be possible. Yeah.
Thank you.
But I think, Maran, I mean, there are not many work in the direction as well, so at least.
Yeah, that's what I kind of noticed. I mean, the challenge with it is that it's, it's not easy to parallelize such a model. I mean, in the very classical, distributed and parallel processing, if things can be decomposed in a way that, you assign, the work or the task to various machines, then it's an easy thing. But in the case of training neural networks, it is really not clear how you just take, say, we have networks with hundreds of hidden layers and
exactly.
very large number of parameters, and yet, we'd like to make real-time decisions on a given test data.
You are giving new ideas. Maybe now you need something like a hierarchical kind of method. Like a this should be a very interesting direction to kind of pursue. Maybe you need something hierarchical, because at some point you get to aggregate those again, right? I mean, the
Correct.
Model parameters. So it could be a multi-layer kind of a learning process, I guess. Yeah. But certainly this is a very interesting idea to think about. And I think this will happen eventually, because the models are too large to run at the base station, I mean, right? I mean, even maybe even a small data set or cloudlet, it can do is too big. So how to distribute it? Yeah, this should be a very good direction to pursue, I guess.
Thanks, Ekram.
Yeah, thank you.
So the next question comes from Koya Sato. Have you evaluated the runtime performance rather than the iteration performance? Because the runtime performance will be influenced by the communication time.
Yeah, good question. Well, I mean, runtime, of course, depend on the system setup, right? The parameters are set up, but you can get an idea about the number of iterations it takes. That kind of that gives you an idea about the overhead and the communication overhead, right? So that gives you high-level idea about how long it will take. So you can see it from the number of iterations it takes for the model to converge. So that's an indication of the runtime, I should say. And of course, the processing time depends on where you are running these, right? But I don't think that terribly, high, at least in this setup here.
So the next question comes from Syed Amir Yosef Hossaini. Is it possible to have a combination of centralized federated learning and decentralized federated learning? I mean, hybrid. I think it sort of alludes towards the hierarchical approach that you just touched upon.
Yeah, I think, I mean, it should not be impossible for sure. I mean, of course, all ideas are possible, right? I mean, now, depending on the problem set up, and as Marwan was saying, I mean, can you really segment the problem, etc., right? I mean, so there could be other considerations, but I don't think it should. I don't think it should be impossible to do, or there should be cases where it can make sense. Yeah, because the distributed one is certainly more challenging. Certainly it's much more challenging. Yeah.
Sure. So the next question comes from Mayuk from IIT Delhi. How is the global model initialized at the server? Is it randomly initialized, or it is initially trained on some other data?
Well, I mean, both are possible. I mean, if you can make a good initial guess, I mean, of course, you can do it, right? Otherwise, you just start from some, initial values. So, I mean, it would be certainly better if you can make a good guess at the beginning, so.
So that it will require less iterations?
Yeah, less iteration. Maybe, some kind of transfer learning. If from somewhere you get a good idea of what it may look like. So of course it's possible. Yeah. Thank you.
I don't have any more questions, but I have from many other attendees, I saw that thank you for the great talk. And from all of us here in the SIG community, in this special interest group, we would like to extend our thanks because this is a very interesting topic. And we need to work on this area. There are many open questions that needs to be answered. So thank you a lot for your time and this wonderful talk.
Yeah, thank you very much, Dola. It is my absolute pleasure, to meet all of my friends and many of my friends. I know many of them, and it's sad that we can meet in person, but I look forward to meeting many of you. It has been an absolute pleasure. What else I can say? Very nice to meet you all. Folks, stay safe and healthy, and we'll meet sometime. Yeah.
Sure. Thank you so much.
Thank you very much. Yeah.
Thanks, everybody.
Thank you, Subha.
Thanks, Ekram. Yeah.
Thank you. Yeah.
Bye.